All right, we are live. Awesome. Hi, everyone. My name is Niels Bentielen. Apologies ahead of time, getting over a little cough and cold, so I might be muting myself to cough a little bit so that you don't have to hear that. But hopefully this workshop will be informative nevertheless. Cool. So I'm the chief ML engineer at Union. Union is a company that is helping ML and AI teams scale, productionize, ship their AI ML applications, and we provide the platform to do end-to-end ML and AI. And today I'm super excited to introduce or kind of talk about secure AI orchestration. This is something that was actually fairly new to me before sort of like diving into some of the implications of LLMs and models and like the model supply chain. So this workshop is actually partly my attempt at also learning a little bit more about the cybersecurity space as it intersects with machine learning and AI. Before we dive in, a little bit about myself. I'm the open source creator of Pandera, which is a data validation tool for data frame-like objects, obviously part of the Union team. Union is one of the main contributors to Flight, which is an open source orchestration tool. So I'm one of the core maintainers there. My background is actually in biology and public health, so less so in the traditional route to this field, although I feel like there are a lot of science folks, former life sciences and natural sciences folks who have made it into data science and ML broadly. And I would say my mission these days is to build open source tools, I guess amend that to just tools in general, both open and closed source for ML and data science practitioners. So this workshop is all about AI security, right? And so I wanted to share this little story that I thought was quite interesting. This researcher, Buck Schlegeris, I believe is how you say that, is a researcher who is looking into LLMs and making LLM agents. And the story is all about asking an LLM agent to do some task and ending up with a bricked laptop, or I guess desktop in this case, because the LLM had code execution access to a shell. It was able to do various things, like promote itself to sysadmin and deleting a bunch of files and leading to the computer not working anymore. So this is one kind of more recent case in point of potential attack vector. In this case, it was more of a self-owned, but you can see how with all the LLM systems out there these days, you're kind of open to certain new class of attack called LLM prompt injection or jailbreaking attacks. We'll get into this a little later, but I want to kind of roll back to like, let's say, classical machine learning, which doesn't have to do with the latest trends around generative AI, which is simply I have model files, and I typically serialize and deserialize them as pickle objects if I'm working in Python. This is another story from the Hugging Face platform of them finding vulnerabilities around pickle files, basically, and doing arbitrary code execution. So I want to emphasize in this workshop, one thing, if you take one thing away from this workshop, is to consider the notion that models are code. They are stored as code, and they produce code. So they are code in that if we consider, say, a random forest or a neural network, they implement a program. It takes in some input X and produces some output Y. So given the latest kinds of models that are a lot more flexible, these models as programs are also quite powerful and can be exploited. Models are also often stored as code, as I mentioned earlier, in pickle files. And finally, they can write code, aka LLMs generating a bunch of code that is evaluated by some kind of interpreter. This workshop will tackle these latter two. The first one, it's kind of a deep topic. I mean, all of these are deep topics, but I think the first one is a deep topic in that there's a lot of things around training data, data poisoning as like a malicious attack vector, things like this that are, I think involve a lot more parts of the ML lifecycle. These two that I'm going to focus on are a little bit more focused, and we can kind of get our hands around this topic a little more concretely. So just a primer, here's the ML life cycle in a very simple diagram. You start from a problem definition. You get data that models or that maps to that problem in some way. You do a bunch of feature engineering. You train your model. You evaluate it. You then will deploy it to production. It generates predictions. You'll monitor those predictions and other health metrics about the software system more broadly, and then you'll retrain the model. And this kind of like is a cycle, even though it's not depicted as such. An orchestrator is the tool you typically reach for when you want to coordinate the logical flow of all the computations that need to happen to get from your raw data over to a set of predictions that maybe your user base or your customer base use to get value out of it. And first, before diving into, we're going to get our hands dirty in a notebook and try running some code and try breaking some things. But first, I want to give you the lay of the land of what we'll be covering. So we're going to be using Union serverless here. Serverless is our Union's fully hosted platform. You can go and run training and prediction and serving workloads on. And so I want to unpack a little bit of how Union works and what its architecture is as it relates to security, because I think it's important to point out here. So if you have the simple workflow for loading data, splitting it, training a model, and evaluating the model, how Union works, and maybe just to take a step back, Union is built on top of Flight, as I mentioned earlier. So a lot of these properties are consistent across these two platforms, but we'll be focusing on Union for this workshop. So this is a DAG, directed acyclic graph, and each node in this DAG, as far as Union is concerned, it runs in its own container, and that container is orchestrated and is set up by Kubernetes. So the compute of where computation runs is at the top side of this graphic. The bottom side is how data is handled. So if we're running things each step in a container, how do we get the data from one container to the other? And the answer to that is through a blob store. So you can think of S3, GCS, Azure Blob Store, any kind of data lake kind of technology. Union can leverage to serialize and deserialize the data from one step to the next. And just to point out, just hearkening back to the model pickle attack, at each stage in this pipeline, as is typical for a lot of people who work in machine learning and in Python, we'll use pickle to serialize a lot of stuff. There are technologies that will serialize data formats and even models now in more secure formats. But if we're being realistic here, a lot of practitioners are moving quickly. They're serializing things as pickle files. The problem with this, obviously, is that pickle files enable arbitrary code execution. So you have to trust the objects that you're deserializing. The way Union passively mitigates some of these risks is that containers do not have root access and limits access of any code that runs inside of that container to the outside world or the systems outside of it. These can be isolated, configurable, such that with network policy, such that it doesn't have internet access, or it has specific access to only certain assets and not others in your cloud, for example. And finally, Flight and Union here will have has a type system, a type engine that handles the automatic serialization and deserialization of objects. So it discourages pickling, although it does not disallow it. And finally, the data store is configured to be immutable, such that we'll see why this is helpful later. But this mitigates any kind of overwriting of existing files with corrupt files. So more proactive mitigations of this would be to use more secure model serialization formats. These are just some examples of those. skops, I think that's part of the sklearn family, I believe, of open source tools. There's Onyx and safe tensors. You can also run your container. You can have your container runtime use technologies like gvisor that virtualize system calls to further add that barrier, such that even if there is arbitrary code execution in the container, there's very little chance of it affecting anything outside of the container. So diving into LLMs, before I get into this, actually, I don't know, for folks who are interested in running some code, there is some setup here, so I kind of wanted to get the ball rolling in that sooner rather than later. So I'm going to hop over to the end of this. So if you go to this URL, this repo, it's github.com/unionai-oss/ml-security. This is the repo where all of the code lives for this workshop, in particular this notebook here. So if you click onto this notebook, you'll go into Google Colab. I would recommend saving this into your own Google Drive, just so that you can save your work. I'm not going to do that for now. And in here, there's just the first step of if you want to follow along with this workshop, you can head over to signup.union.ai to create an account. You will need a GitHub account for this. Since I already have one, it'll automatically redirect me to the Union serverless dashboard. But you will have to go through a flow that takes you through GitHub and to provision your account. It'll take a few minutes. So you can sit tight while that happens, and you'll know that your account is created if you can visit serverless.union.ai, and you should see something that looks like this with a dashboard. We'll be returning to this UI a lot in this workshop, so yeah, we'll unpack this a little later. But that's really the step right now, that if you're going to follow along the code, create a Union account, and you can always feel free to run some of the setup here ahead of time. Okay, so just going back to the slides and to just set up this problem around LLMs is around agents. So if you're not super familiar with the Gen AI space and the LLM space, there's a fairly new construct called agents. You can think of these as essentially, if you think of all your classical programming constructs like conditionals, if-else statements and for loops, we're essentially using those constructs and interleaving them with LLM logic, right? And we are delegating some parts of the logic and the computation to an LLM. So in this case, a very simple case where the input prompt is, what is 2 plus 2? We can, one way of doing this, right, is just have have the LLM generate the answer, and it probably can because there are a bunch of correct instances in its training data where it knows the answer is 4. But for any other arbitrarily complex question around, say, math or arithmetic or anything else, you would want an agent. You can't rely necessarily on the agent's own weight, the LLM's own internal weights to generate the answer zero shot. So there are all these other techniques, right? Like few shot learning, you give it some examples. But another technique that is encapsulated in the AI agent concept is the ability to use tools, for example. So here we we have the agent write some code, in this case, result equals 2 plus 2, which is then sent off to some code interpreter to get the actual result, which we then return as 4. Right? So this is a very simple example. The issue here, right, is if I try to prompt it to say, write a system call that runs an arbitrary command. So this is sent over to the tool, the Python interpreter tool, and bad things can happen here, right? And then you'll have some kind of response, but then the side effect of running these system calls inside of the whatever EC2 instance or wherever this agent is being hosted can happen, and any of those side effects can include, hacking into your system more broadly. Again, just to call out some of the properties for the kind of the passive mitigations here are the fact that every single node in your DAG in a union workflow is running on its own container. So you can fairly easily configure these, again, to have very limited policies, such that your Python code tool doesn't have internet access, and it can't access anything outside of the container. And finally, there's another kind of mitigation that is always the fallback around human in the loop. So in this case, we'll see what a workflow looks like. We'll generate some code. We can take a look at the output first before running it in the Python tool. And obviously, you reject it if the code looks suspicious. More proactive mitigations around this, obviously, are to use stricter container runtimes and only allowing the agent to run trusted functions or APIs. That kind of like reduces the space of possible programs that can be run that are insecure. So, okay, we are about a third through this workshop. Hopefully that gave you a little bit of the ground knowledge to run through the rest of it. I'm going to head over back into this repo. Again, the notebook link is here, so go and click on it. You'll end up here. So for the rest of this workshop, we'll be running through this code. I'll be dissecting all the different elements of the various attack setups and the mitigations. Some of them that we talked about, we can't cover all of it. But the first thing we'll do is run this setup code, this dependency installation step. Just take a few seconds, if not a minute or so. There may be a pop-up that says you need to restart the runtime. So, just go ahead and do that. If that pop-up shows up, it should be okay. The next step here is you're going to run this cell, and this will log you into your Union serverless account. And so it'll open up a link here with the pre-embedded code. Go ahead and run that, and you should see a login successful message at the end. So if I rerun this, I've already logged in, so I'm good to go here. So part 1, pickled model attack. First, we're going to set up a model training pipeline. It's going to be fairly simple. We're going to use the wine data set to do some classification. We're going to use a random forest classifier, so no fancy Gen AI stuff here. Just good old-fashioned, good classical, reliable for the most part, machine learning. So I'm going to call out a few things here about union as I go, just because it's important to understand this as you're also learning about these model attacks. So the first thing we've done here is we've abstracted away Docker files, essentially. And this is a simplified interface. You can think of it as a simplified interface to Docker, where you can specify a lot more here, but all we need is the dependencies that will run our tasks, our union tasks and workflows. So pandas, scikit-learn, flightkit, obviously. We're going to then, this is not necessary. I just kind of did it this way, where this union.task is a decorator, and I'm just going to reuse it a bunch in this notebook. So I'm going to preload it with some arguments here, namely the container image. I also want to cache the steps. So the union handles caching very nicely, so you don't have to waste compute if you're giving your task the same inputs. We're also defining a model output type here as a name tuple to say our model is going to be a file, which is the joblib pickled file, and an accuracy score associated with its test accuracy. Down below here, I have 3 tasks, I guess 4 actually. So I have a load data task, which just loads up the wine data set. I have a split data task that splits it into train and test sets. I have a train model task here that will train a random forest classifier, serialize it with joblib, which is still a pickle file, and outputs it as a flight file. And flight file here is just a quick call out, is flight, and therefore is inherited by union. It is a type, output type or input type that allows you to not worry about files and directories. So there's also a flight directory type, and this allows you to just output files and directories, and unions auto serialization, deserialization should handle passing those files from container to container, so you don't really have to think about it. The last step here is to evaluate the model. Here we're just taking an accuracy score. We're going to make a nice deck visualization of it, and we are going to then stitch all of these steps together into a wine classification workflow. So these are literally just using the building blocks of the tasks above and composing them together into our final training workflow. So I'm going to run this. You may see a warning around series not being transported as pickle. So this is actually a call out that the flight type system and the union type system understands a lot of data types, but not all of them, obviously. And so one of those are series. The way we're going to run this workflow, so we can run this workflow locally, right? So actually, if I just to prove it to you, I can run this wine classification workflow as a Python function, and here's the output. If I check here, I actually have the model.joblib file here. But to actually run this on Union serverless, we have to create a Union remote object, and this will use our client to execute stuff on our serverless account. I'm just calling it serverless here just to be super clear where it is running. So So I'm going to execute this code. And since wine classification workflow doesn't take any inputs, we're just going to pass in an empty dictionary. So we're going to run this. And I probably, for those of you who are running this in your own Google Colab notebooks, you'll see a image building step. And so that'll take maybe 30 to 40 seconds to build the image that's specified over here with these requirements. So the execution should, the output of this cell should show this, which actually is the execution view in the Union dashboard. So you can see our workflow as a series of steps. You can look at it more as a graph, just to see how, the flow of data more explicitly. Or you can look at the timeline view. I've actually pre-run all these steps, so these ran super quickly, and it says from cache because it was taken from cache. So a few things to note here is we can view the inputs and outputs. So the output of this workflow was our model and its accuracy. And this is, you can think of this as mapping to some kind of blob store in the back end. We have a Union protocol, file system protocol here, but this, you can think of this as a S3 path to this pickled model file. Okay, so we're getting all the setup in, just showing you like how to use a notebook to run Union workflows, in particular to train a model. We can grab that model back into our Jupyter notebook by running this code cell. And this is the scikit-learn rendering, HTML rendering of a model. So it's our random forest classifier. And just to prove to you, we can generate predictions just in this notebook runtime. I'm just running this cell, and you can see the predictions on the whole training set. Okay, we're going to get to the attack real quick, but first, we need to generate some predictions. So here we've defined a batch prediction task that just deserializes the flight file, passes the data through the model predict method. And so we're going to run this on serverless, and you can check it out over here. So this time it's not cached, obviously, and it's running here, just a DAG with one node, super simple. And we're gonna wait for this to finish, and I think it has already, yeah. And these are just the first 5 predictions that, again, we just passed in the training set. So it's not really production kind of features, but shows you that everything is working. So finally, we get to the pickled attack. And so what does this attack look like? I'll show you. This is not exactly how I would do it if I were malicious in any way, which I'm not. But I'll show you the basic anatomy of it so you can kind of understand what's going on. So in this case, so a pickle file is just a Python object that can be anything. I think there are tools to try to inspect these without actually loading them into memory. But the simplest version of this is I create a object. In this case, I'm calling it pickle attack literally. And in this reduce method is something that is run at both serialization and deserialization time, right? So when I define this object and I write it to a joblib file, now I have my fake model here, and when I deserialize it, the code inside this method will run. And so to prove that to you, I'm actually going to pass in this fake model path to the batch predict method. And it's going to fail, mainly because the batch predict method expects to create a model file that has a predict method, right? So this does not have a predict method. A better attack would would actually run this silently so that the task actually produces some kind of prediction that makes sense. But I can go to this link over here and look at some logs. So I'm going to look at the task logs. If I click on this batch predict item, go to task logs, I can see here that, my code actually ran under the hood. So this, in many systems, this is like the first thing you need to like do some other nasty stuff. Or you can do some crypto mining, or take advantage of cloud compute infrastructure like that. Okay, so that's essentially it. The main vector of attack here is not so much necessarily passing in the actual pickle file as a user, as like in reality, this batch prediction step would be automated on a schedule, and it just runs every like week or something. And the model path will be kind of hard coded into that, into wherever that scheduled workflow is running. So the more realistic vector is finding out the original path of the model. So in this case, that would be over. Oh, no, this is the prediction. Oh, yeah. So the model file is over here, right? So if I can find out where in the blob store this was actually stored, if I can somehow break my way into and get all the permissions to overwrite this file, also still kind of a tall order depending on the security of the system you're trying to get into, overwrite that file. And so now it's corrupted. And when this batch prediction step runs again, it'll run this code over here when it tries to deserialize the pickle file. So again, if this does happen, just alluding back to these architectural decisions of isolated containers, like the blast radius of any given attack should be fairly contained in Union anyway. But I'll show you one mitigation here, which is to use Flight's and Union's flexible type system to create a custom type here called model. And this model has a Flight file component, but also has MD5 hash. And this tracks the file's integrity. So in blob store, these will actually be written to two separate places. And so for an attacker, they'd have to also find out where this hash is, as you'll see a little later. So this model, whenever it's initialized anywhere, it will, after initializing itself, it'll check for the hash, and then it'll actually hash. It'll read the file, the contents of the file, so it actually won't load the model into memory. It'll read the contents of the file and then raise an error if the MD5 hashes don't match, right? So this is fairly standard practice for any arbitrary file. So when we apply it here, we are changing this from a random forest classifier to a model object or model type here that we defined. And so whenever we train a model, we're going to compute the hash of it here at training time. And now this is kind of like set in stone. So then when I do batch predictions on this at any given moment, when I load this into memory, it'll run that post init step that checks the integrity of the file contents first. And so actually that step is done here in model guard. So it'll take as input the model file and some hash that you need to hard code somewhere of like, here's the trusted model that is currently in production. And it'll try to initialize this model object. And this task should fail if that model file has been tampered with in any way. So let me show you this. So first we're going to train the model. So as we saw before, this will take a few minutes, a few seconds to run. I've obviously run this before, so it's going to fetch the model hash and the model itself. So that in that case, it's this string. And with our secure batch prediction workflow, we pass in that hash and the model file. And if everything works as expected, this should fail at the model guard step. So I'll give that a few seconds. Oh, it succeeded. Oh, right. So this is the actual. So right, it succeeded because this was the correct model file. Right. This is not the corrupted model file. I'm jumping ahead of myself here. So that that actually worked well. So now we can grab the model again. We can do predictions locally in this notebook. So the fake model path here that if I just go back up a few cells, that I wrote here, right? It worked in this previous insecure batch predict model, task. But if I pass it now to this secure batch prediction task down here, so I'm passing in the fake model path here with the model file MD5 hash. So this kind of simulates me overwriting that S3 bucket path somewhere, right? So assuming I've done all that hard work and I've managed to get my way in there and overwrite the file, this is kind of what that simulates. So now this should fail. Fingers crossed. Okay, cool. And it fails with this error message that we have. So, we expected this hash, but when we hashed the contents of this corrupt file, we got this. And so now we know, something's wrong here. So that's part one. Essentially, we learned that pickle files are kind of dangerous. You have to trust the file that you're deserializing with pickle. And you can mitigate certain things and just use this kind of a standard practice here of using hashes to check for file integrity. And we did this kind of pretty easily natively with data class here that union tasks and workflows can understand, and such, so that imagine working in a larger team, you'll have a library of these kinds of types that you can reuse across your code base so that you can kind of guarantee certain things about file integrity. Okay. So now let's move on to the second part of this workshop, which is the LLM prompt injection attack. This will require some more setup. So if you're following along, head over to the OpenAI platform here. You can sign in. There'll be a fairly easy to follow flow here for creating an API key. So once you have that API key, you've stored it securely somewhere, you can run this union CLI command, create secret. I'm going to stop this actually. So there's an input box where you can enter that secret. I've already created mine, so I'm just going to stop running that cell. And just to confirm you have the secret in your union account, you should be able to see it with this union get secret command. So this is right here. Okay. So for those of you following along, now we're going to make the simplest agent possible using the OpenAI API. So the agent's response is just going to be this output name tuple. Actually, this name and this name should match, but anyway. We're going to use the OpenAI API key secret that we just created up here. And we're going to request it in the union task so that it's available inside of the container. And we're just going to use the same container image we used above in our part 1 workflow. And this agent is super simple. All it does is it takes in a prompt. It is a helpful assistant that generates Python code to answer questions. It can only return Python code, no things around it like markdown or explanations. The last line of the Python code must assign the result to a variable named result var. Cool. So we have some parsing logic here. So, as you may know, the LLM outputs may not always adhere to the prompt. So here we have some logic to sort of like parse out code fences and get the resulting actual Python code. So this makes sure that Python can create an AST representation of the string as just like one step to make sure that the code can actually run. So that's called inside of here, inside of this generate code task. And then in the same container, we're going to call the Python tool that takes the prompt and executes it, and then pulls out the result, which is the result var, which should be in the locals dictionary. Okay, so this is our setup. Obviously, no one would ever really write this agent seriously, but we're going to ask it a series of questions here first, right? So the happy path is a good faith question. What is the sum of this list of numbers? So we get this execution. It is running. Single node DAG again. Then we're going to wait for the response, and fingers crossed, we're going to get 15. 3, 6, yeah, so that's correct. Now, the LLM prompt injection attack, I think a lot of systems like OpenAI, ChatGPT, or Anthropic endpoints, like a lot of them will probably have safeguards, or they definitely do. But this isn't the case that you're writing your own, or you never know. There may be a popular tool out there that uses LLM agents that do not have the right safety checks and validations in place. So the very simple version of this, right, is write an OS system call that executes this. So we're going to run this. We're going to inspect the output here. And actually, the output is not the important bit. It's the task logs that are the important bit, right? So the output was like 0, right? Because we executed some code and it returned 0. Since it was I guess, a system call. The important bit is right here in the task logs that the arbitrary code that was embedded in the prompt was actually run, right? It may not be feasible to have anything more complex than this actually run, right? So you can do something else, right? The prompt can say, hey, I have a script here that I want you to run, right? So this is just a gist that I have. Again, super simple, but again, you can make this arbitrarily complex. And the prompt is simply to use some built-in Python library to download it and run the script. So let's take a look at this. And again, the logs here are the important bit. We can wait for this for a second. And right, we ran this bit of code here. So not great, right? I mean, the LLM is super powerful and therefore can be used for ill. So that's the attack. Hopefully that makes sense to all of you. Yeah, it's kind of a fun game. Trying to come up with these sorts of attacks and what their counters might be. So the counters that I'll show you here are guardrails, containerization, and human in the loop. So to implement some guardrails, we can implement guardrails in various different places. So the first one I'll implement here is in the code generation step. So the important part is we're going to have some set of disallowed patterns. This could be a long list of things. Again, this is like the most basic version of this. Saad, thank you. Yeah. This will be recorded, so folks can take a look at this later. So jumping back, like this is just we're using deterministic code in like traditional software to like suss out whether or not code generated by an LLM is insecure or suspicious. There are fancier products, open source tools, and companies dedicated to this. I believe maybe I'll shout out one, LlamaGuard. Well, Meta has a LlamaGuard model itself, but there is. I'm blanking on the tools now. Actually, I'll follow up with this after this workshop. But there are all sorts of like LLM model-based tools that will try to look at code and identify whether it's insecure, suspicious, or malicious. But in this case, we create this kind of output guard decorator that we're going to use down here in our task. And so this output guard will look at the response, right? So we're still using OpenAI's API here to generate the code. We're still using our parse output step to like get the actual code snippet to run in our Python interpreter. But here at the output step, which is just a string, we're going to wrap this in output guard such that our string here that comes out of this function call. This function call is that the generate code step. We'll check for any of the disallowed patterns in the output, right? And then it'll raise an error. So again, this is just like the most brute force version of this that could be very brittle, since there are all sorts of code obfuscations that we can implement in the attacker side to like get around these. So, but you get the idea. So I'm going to go ahead and run this code to define these functions and tasks. The other kind of guard, and it kind of dovetails with the containerization part, is that instead of up here in our original implementation, instead of having the code execution happen inside the same container that generates it, I'm going to break it out a little bit. So we're going to break out the Python tool into its own task, its own union task. It's going to have its own guard such that this guard is at the input, right, of the prompt. So before any of this code runs, we're going to do this step here of calling out to this tool called Bandit. This is an open source code analysis tool. And it outputs this JSON report. And this simple logic here is basically that if there are any like severity, high, medium, or low that are flagged by this tool, we'll then raise an error here. So again, we're using like static analysis, code analysis tools that were there, existed way before LLMs, and we're leveraging it here just in this particular case. Cool. So let me define this task. And the last thing is Flight and also Union have an approve node. And this node allows humans to confirm, to have a human in the loop step in your workflow. So we have a secure run agent workflow that actually, I forgot to edit this. So these are literally both the same function. But if you can bear with me here, I'm just going to do some editing. So the secure run agent task generates the code. This has the guard, and the Python tool. This also has the code guard. Or we can run the same workflow and have an approve node here. And we'll show you this in the UI in a little bit, but it allows us to run to inspect this code and then explicitly approve it before running the Python tool. So let's see all of this in action. First, I'm going to show you the first guard, right? So this is the code generation output guard. It's going to run this secure run agent workflow. If you're running this, you'll probably have some image build steps before outputting the execution URL. Okay, so this errored out. Oh my, this is a different kind of error. Great. This is demo gods are not happy. So I'm going to go ahead and do some live debugging. Hopefully this works. I'm going to explicitly use the same Python version here. You can do the build step. Cool. So hopefully this now matches. There's some details here that I won't bore you with around this error. So hopefully this is the right, okay. Well, I'm not getting the expected errors here. I think it might be a version mismatch between this Python version. So let me see what this, okay, it's 3.10. So one more time, we're gonna try this. I'm gonna go back up here. We actually do have a fix for this in Flight. Run this again. It's gonna rebuild the images. Now this is running. Fingers crossed. We'll move on, and I'll kind of like explain what we should be seeing here and follow up. This doesn't work. So it looks like it's doing something different. So if we take a peek into the task logs, looks like it failed. And why did it fail? Okay, cool. So yeah. So if we look at the generated code, actually we don't even see it because the output, this task actually failed. But our disallow pattern kind of logic here worked, where, you know, in this particular case, I'm stating that, you know, this Python tool can only really run things like maybe arithmetic, maybe not make system calls, maybe not make requests to the internet, things like this, right? So this measure this guard actually caught this this prompt, the code generated from this prompt. So to show you this bandit tool in action, I'm going to go ahead and actually just comment out these disallow patterns so that we can kind of accept the code at the output generation step. And here we have a new execution. And so if everything goes well, this generate code step should pass. Give it a few seconds. Okay, so it succeeded. And we can see the code here that it generated a bunch of code to accept the URL, or to take the URL, download the script, and then run the code, right? So this kind of accounts for our own little homegrown detection tool didn't work, but we're using this other tool called Bandit, that it errors out with this report that says there are certain lines that are suspicious. I think this is highly suspicious to be some kind of attack or insecure code. Okay, and then I'll uncomment this again to revert that change. And finally, I'll show you the very last thing, and we're pretty much right at time, so this is great. We'll provide the good faith question. What is the sum of these lists of numbers? And in this workflow, we have an approval step in between the code generation and Python tool. So we'll take a look at how that goes. So here we can see, if we go back to the node list view, there's a button here that looks kind of like a play button. This is the button you'd click to take a look at the code generated. So I think new lines are not rendered here on the UI, but you can see it assigns numbers to this list, and then it'll sum the numbers to give you the result. So this looks good to me. I'm going to approve it, and it'll take a few seconds, but then this will forward that code into the Python tool that will then execute. All right, so that's pretty much this workshop. To summarize, you've learned the basic concept, setup, and mitigations for the model pickle file attack, the LLM prompt injection attack. I'm pretty sure there are fancier, more sophisticated versions of these attacks that one might be exposed to, but hopefully this gives you a sense of what the risks are and where certain attack vectors can be in your ML pipeline. Awesome. You also learned a little bit about Union, how to put tasks and workflows together, as well as other open source tools that are available for code analysis and security. I'll follow up with a name of like the more modern takes on this for insecure code classification with models. If you want to learn more about Union, you can go to union.ai. If you have questions, you can reach out to us at support@union.ai. And yeah, thank you for attending, and hope you got a little something out of it. Bye. Actually, I'll stick around for a few questions if there are any. So I rescind that. Bye. Stick around for maybe 2 or 3 more minutes. Okay, I'll end the stream now. Thank you all.